In this video on solving basics for trig equations, we're going to look at the equation cosine theta equals 1/2. Now, if you're familiar with finding exact values, you'll find that solving trig equations, especially the basic trig equations, will feel very similar. You use a lot of the same skills, but you're just kind of working in the opposite direction. So something I like to think when solving an equation like this one is which angles have a cosine of 1/2. So if you know your exact values, you probably already know that. And this way of thinking and just having an overall strategy tends to be very, very helpful. All right, so let's look at an outline for how we can solve. The first step is going to be our analysis. We're going to figure out which quadrants our angles are in, and then we will build our reference triangle. And that together will allow us to complete step 2, where we actually determine our angle answers and represent them in whatever final form we want. So let's do this for cosine theta equals 1/2. So step 1 is to analyze, and we're going to find out which quadrants our angle answers should be found in. And we'll do this using the acronym ASTC. I think all students take classes. And we're going to label our quadrants with these letters, and these letters will help us recall which trig functions are positive in each quadrant. So start in quadrant 1, label around ASTC. So a quick overview, we know they're all positive in quadrant 1. Only sine and its reciprocal cosecant are positive in 2. Tangent and its reciprocal cotangent are the positive ones in quadrant 3. And it's cosine and secant that are positive in 4. So look back over to our problem, and we see we want cosine of an angle equal to positive 1/2. So we need to be working in the quadrants that have positive cosine. So of course, they're all positive in quadrant 1, so we'll have an angle in quadrant 1. Let's go ahead and sketch that out. Just a quick angle there. We're sketching the terminal side. And we said that cosine is also positive in quadrant 4, so we'll have another angle answer there. Now that we've determined our quadrants, we can move on to the other part of our analysis, our reference triangle. And so we need to be thinking which of our special right triangles has the x coordinate, remember that's the cosine on the unit circle, cosine and x coordinate, of 1/2. So I like to think that's the shorter side in those special right triangles. So the horizontal leg of the triangle should be the shorter one, as opposed to, say, square root of 3/2. So that means the longer vertical leg here. And we're dealing with that special right triangle that has a 60-degree central angle. So that I call the 60-30-90 special right triangle. If you need any review with those, I'll post a link in the video description, and that'll take you to some unit circle basics and some videos that go through the special right triangles and their properties on the unit circle in detail. So check that out if you need it. But otherwise, here we have our triangle. It's a 60-degree central angle, so that's going to be our reference angle. And instead of saying 60 degrees, most of the time when we're solving trig equations, you want to be in radians. And so the equivalent angle in radians is pi/3. And so what that's going to tell us for step 2 is that our reference angles, or just the amount of rotation from terminal side to x-axis, is going to be a rotation of pi/3 radians. All right, so now that we know that, we can actually find our angle answers. In the quadrant 1 angle, let's look at that one first. It's going to be very easy. We simply rotate like this. We know we just said that that was the reference angle pi/3. So one of our answers on the unit circle is going to be pi/3. That's the one from quadrant 1. And now we can work on calculating our quadrant 4 angle. So to do this, we basically know we've done almost a full rotation, almost to 2 pi, but not quite. We've done pi/3 less than that. So instead of writing 2 pi, let's represent it as 6 pi/3, so it has a common denominator with our reference angle. And all we have to do is subtract our reference angle from 2 pi, or 6 pi/3, to get that angle that we want in the 4th quadrant. Okay, so of course 6 pi/3 minus 1 pi/3 is going to be 5 pi/3, and you've got your second angle answer. And these I call answers on the unit circle, or on the interval from 0 to 2 pi. Eventually, when you have a lot of practice with solving trig equations, you'll simply know that the quadrant 1 and quadrant 4 angles with pi over 3 reference angles are these two, pi over 3 and 5 pi over 3. So for now, we kind of showed how to determine those, but eventually step 2 will get very, very quick for you, and it's as simple as writing down the answers. One more quick thing before we finish. If we said we want to find the answers, but for all solutions, we can write a really clever equation solution. And it will represent the two angles that we stated above. We'll have two separate equations, but also all the coterminal angles. Because, for example, say pi over 3 is coterminal to 7 pi over 3. Well, if you find the cosine of pi over 3 or the cosine of 7 pi over 3, both of those are going to equal 1/2. So they're both solutions to the equation. And so to represent that, all we have to say for each of our angles that we found, we say that theta can be pi over 3 plus 2 pi k, where k is an integer. And remember, 2 pi is a full rotation, so this is a really neat way to represent an angle and all its coterminal angles. All right, and then of course we would write another one for that quadrant 4 angle, 5 pi over 3 plus 2 pi k. And some people like to use n or some other letter as their variable. Whatever works for you is great, and this would be the solution to our equation, cosine theta equals 1/2 for all solutions. So that's all there is to it. Hopefully this helped you establish a foundation for solving basic trig equations and gave you a good strategy to follow. I'll post links to more worked out examples and some other unit circle tips in the video description, so check those out, and thanks for watching.